Okay, let's look at the problems from recursion. There are quite a lot of here, so I picked from 6 only 3. So the first one, B, 6b, was we defined f0 to be 1, f1 to be 0, f2 to be 2, and fn to be 2 times fn minus 3. Okay. And this last one is for n at least 3. Let's check that this is well defined. If n is at least 3, we refer this is the recursion, right? So this is somehow the basis, or basic step, and this is the recursive step. And n has to be at least 3. Now, if n is at least 3 and I subtract 3 from it, then the result is at least 0, and that's okay, because I know what happens for these numbers. So for every number, this is now defined. Here, this is defined for 1. Here, the definition is for 1, 0, 1, and 2, and here is the definition for all other n. Okay, so that's well defined. So what they ask us to do now is, well, is it well defined? Yes. Okay. And secondly, okay, I said it in words, but you have to kind of spell it out, of course. Not that I'm going to ask you to do that, so that's why I've not bothered too much about it. So the next thing that they ask you is find a formula. So let's try to find a formula. Now, how do we do that? We don't have the techniques yet to solve this. This is something from a later chapter. So we have to try, okay? And so we can start building up our things. Let's calculate f3. There's no need to start from a higher number. We have to go all the way up anyway. So f3, so what is f3? Well, it is 2 times f3 minus 3, right? So I'm using my formula. N is 3, so replace n by 3, so this becomes 0. What is that? Well, f0, that is given, right? We know what that is 2. Okay. What is f4? f4 is 2 times f, now subtract 3 from 4, so f1. But that is 0. Right? That is here that I use that. What is f5? f5 is 2 times f2. Okay? So what is f? With f2 we know that is 2. So this is 4. All right. At this point there's way too little information to have any, I hope, for a pattern. Let's do f6. f6 is by the, so we are, with all these numbers, we always keep using this recursion rule, right? So f6 is 2 times f3. And we know what f3 is from this line. We know it's 2. So this is 4. What is f7? Well, f7 is 2 times f4. But f4 is 0. So this will also be 0. f8. f8. That we have to go subtract 3, so we actually have to look at what f5 is, and f5 was 4. So using this, we find this is 8. Okay, so we see 2, the pattern is 2, 0, 4, 4, 0, 8. Let's go on. f9. 2 of f, subtract 3, this is f6. And f6 is 4, so we multiply with 2, so 2 times 4, that is 8. Okay? All right, f10. Any guess what this would be? Well, f10 is, you subtract 3 from it, but if I subtract from it, I fall into this guy here, in f7, which is 0. And this is something, if we start thinking about this 0 is going to keep coming up. Every third one, this will be 0, right? Because if you go 3 down the list, you find another 0, and you're also multiplying with that number, right? The formula is multiplication here. We multiply, so each time we put in a 0, the result is also 0. So this tells me, let's use this in a, so we can make this conclusion already at this point. What is this? Every other 3 this is. So this is for 7, it is for the numbers 10, 7, 4, and 1. Now we have a way from discrete 1 to formulate this properly. This is that your equivalent, the equivalent with 1 mod 3. So if n is equivalent with 1 mod 3, remember this means that if you subtract 1 from the number, it's divisible by 3. So in this case, 10 minus 1, that is 9, right? 7 minus 1 is 6. So in other words, the numbers where we get 0, so what we can already conclude that f of n is 0. So that's okay. Well, I'm going to postulate this. We're going to have to prove everything, but I think I have a formula. So in this case, so if n is equivalent with n mod 3, then f of n is 0. That's my postulation. I still write a little question mark because I haven't proved it. I have figured it out. I think I'm right, but I'm going to prove this later. But that doesn't solve the other two, because that's not what happens there clearly. f11, let's see, what is f11? Well, it is the same as f8. So you see, it's always with 3's that we go, right? And so what is f8? That is 2 times 8, that is 16. So what is f12? So far the pattern was, let's look at this. Let's start coloring things. So I'm sorry, I'm going to do it with this thing. So the ones that are equivalent with 1 mod 3, let me make this a bit wider. The ones that are equivalent with mod 3, let's mark them in orange. That was this one, this one, this one. Okay, so the next one will be f13. So what are the... Let's look at another pattern that always keeps getting, because it works with 3. So the multiples of 3, let's look at these. f3, f6, f9, f12. What is happening there? So look only at the greens. What are the solutions? But we haven't done f12, so we should have actually done that. But I was trying to already anticipate what it would be. Let's see whether we can guess it, and then it's better even if we can guess it now correct, the more likely that our formula is correct. Okay? So let's see. Okay, so 2, 4, 8. So it's always powers of 2. So this should be, again, 2 further. So this should be 16, right? Is this 16? Well, the formula is 2 times f12 minus 3 puts you in 9, which is the previous green one, which was indeed 8. So there's 2 times 8. So this is 16. So that is correct. Yeah. So, oh. Okay. So we seem to have also think about a formula of this nature. So let me do this again. And so it remains the last one, right? Let's do this in purple. 5, 8, 11. The next one will be 14, right? What is happening there? Exactly the same, also powers of 2. Each time geometric series, in other words, you always get twice more. So we have f13, f14 here. So let me write this. So this is f13. F13 we know already what it should be. It should be 0 because we are in the orange style. F14, that we are anticipating it should be 32. Well, let's see. It should be, by the formula, it's 2 times f14 minus 1 is 11, and f11 is 16. So it's 2 times 16. So it's exactly what we said it would be. Okay? So just to make sure that this is 0 and this is correct, right? Because if I go 3, f13 is twice the f10, but that's a 0. So therefore this is also 0. Okay. Okay, so we have some ideas what happens here. The tricky part is now to write this up properly. What are these formulas? So it is clear that the division depends on the residue mod 3. Right? The orange one was n equals n equivalent with 1 mod 3. So what's the green one? The green one, oh no, sorry. The green, no, yeah, okay. The green one was n is equivalent to what mod 3? 0 mod 3, right? Okay, so n is equivalent to 0 mod 3. What is happening then? Well, it seems we get a power of 2. Now is the question, which power of 2? Okay? So if n is a multiple of 3, that means, let's look at what is this. So here n is 3, and the power is 1. Okay? Here n is 6, and the power is 2. It is n squared, 2 squared. Okay? Which is 6 divided by, 4 is 2 to the 2, which is 2 to the power 6 divided by 3. This is 2. It is 3 divided by 3. 9. 9 is 3 times 3, right? So this is 2 to the third. So what we're thinking is, in this case, the formula should be that. The exponent of 2 is you take the index and divide by 3. For instance, here, F12. So what it says, divide 12 by 3, get 4. That should be the exponent of that 2 to the exponent. 2 to the 4, that's exactly 16. So here's my conjecture for this case. And then for the orange case, we can also work that out. Do this quickly. So, sorry, this is the orange case. No. I mean, I said orange and I meant purple, of course. So this is n equivalent with what? The only thing that we have done is n mod 2, right? Equivalent with 2 mod 3. Mod 3. And so what is the expectation? Again, it's a power of 2. We have to figure out what exactly is the exponent. Well, let's look. For 5, the exponent is 2, right? So for 5, the exponent is 2. For 8, the exponent is 3. For 11, the exponent is 4. How do we get to these numbers? Well, 4, it has to do with multiples of 3, right? So if I take 11, if I take actually 12 and divide it by 3, that's the power. By the way, actually another way of saying it is that actually the 2 consecutive ones are always equal, right? The purple one is equal to the next one, the next green one. Yeah. So in our formula, this would mean that we take add 1 and then divide by 3. n plus 1 divided by 3, and that power of 2. Let's just double check it for 1. For 11, so what it says, add 1 to 11 and divide by 3. 12 divided by 3 is 4. 2 to the 4, yep, that's correct. That's my formula that I suspect is true. Now we have to prove this. Okay, so it's a kind of a long question, right? But I'm going to go quicker on the other one. So proof. Well, there are 3 cases, so I should treat each case separately. That is the hard part with this kind of recursion is. So we have case 1 is, let's do the green one first, that n is equivalent with 0 mod 3. And then my prediction is that f of n is 2 to the n. Oh, I'm sorry, I was writing this on the wrong spot. I hope you figured this out. Sorry. This I had already figured out. It was that, right? It's this one here. Sorry, I was thinking, how come this all of a sudden changed? Okay, sorry. These are my 3 predictions, okay? So I'm expecting this to be true, okay? Base case. So n is equal to 0 mod 3. What does it mean? This is not helpful in writing it that way, but it means that n is a multiple of 3, right? That n is 3k, okay? And so n divided by 3 is just k. So I'm saying that f of n is 2 to the k, okay? So now I want to prove this f of n plus 1. Sorry, yeah, no, if the way I set it up, let me set it up correctly, sorry. I'm going to set it up that it makes it, because now I'm not going to ask you to do this case by cases, so I just wanted to show you how it works by cases. It's trickier. So what I'm going to show is, okay, I'm going to show that the formula is given by these 3 cases, and we do strong induction on n. Now the base cases P0, P1, and P2 have to be treated separately, but they are correct, right? Let's see that the formulas are correct. If n in the case f is 0, what kind of color is this? This case corresponds to, it's the green case, right? It's a multiple of 3, and then it should be 2 to the power 0 divided by 3. That is 2 to the power 0, it's 1. So this is correct. So this case already works. What about P1? P1 is now the statement that P1, sorry. So let's verify P1, okay? I'm sorry, I'm getting P1. P1, we are in this situation. So we have to apply this formula. And this formula says if you're in this situation, the result should be 0. Is this correct? Yes, it is correct. So again, we had done with this one as well. So this is correct. We had already done the previous one. Yeah, let me just put the check mark here. Now, last one. What about P2? Is P2 3? Well, which of the cases are we? We're clearly in this case, right? And then the formula says, so now P2, let's write down what P2 should be saying. P2 says that f of 2 should be equal to 2 to the 2 plus 1 divided by 3. Right? This is what this formula says. Okay. Which is what? Is 2 of 3 divided by 3, that's 2 to the power 1, that is 2. Is this the case? Yep, that is the case. Okay, so the 3 base cases are done. So now, the induction step, or induction hypothesis, let me write that down. The induction hypothesis is that Pn holds for all values at most n, and so to show it also holds then for one more, Pn plus 1. Okay, so proof. So, and now we have to divide by cases. N plus 1. Case 1. Let's assume that n plus 1 is, we have to now see in which of these 3 cases are we. Okay? All right, so case n plus 1. We can make now, okay, let's take the case, okay, sorry, n plus 1. So the first case is that n plus 1 is equivalent to 0 mod 3. That's the first case, case 1. Case 2 will be that n plus 1 is equivalent to 1 mod 3, and then case 2 and case 3. Okay, I guess should have numbered them a little bit differently, but okay. 1, 3, okay. In each of these 3 cases, I have to check what happens. Okay, so let's check out what is Fn plus 1. Now, it is easy. The formula for Fn plus 1 is we have a formula. There is only one formula. It's this formula. This is the formula, right? So, okay, we say it's the same as Fn plus 1 minus 3. That is f of n minus 2. The problem is I have the formula for fn minus 2 depends on which of these 3 cases I am. In which of these 3 cases am I in? Okay, so let's see. But let's start with in this case. If n plus 1 is 0 mod 3, if I subtract 3 from it, it will also be in this case. Okay, so subtracting 3 will not get me out of one of these cases. So, all right. So the cases were, if I'm in this case, then this is given by, sorry, I claim it to be, in that case, given by this formula. Okay, 2 exponent n minus 2 divided by 3. Oh, sorry. I apologize. I put in the formula wrong. Fn plus 1 is twice Fn plus 1 minus 3. This is twice this, so it's twice that. So that is equal to, how do you multiply these things? Well, that is, multiplying is actually an exponent 1 here, so it's 1 plus n minus 2 over 3. And put this in common denominator, so that is 3 plus n minus 2 over 3. That is, sorry. What is it? 2 to the power. So this is 2 to the power n plus 1 divided by 3. Okay? Is this what I want it to be? Well, in the green case, the formula should be you take the exponent. My exponent was n plus 1. And you divide by 3. Okay? This is the formula. But be careful. Here we worked with an n, but now we have an n plus 1, right? That's the difference. So now we have, indeed, n plus 1 over 3. It's given by the right formula. Okay, let me go quickly to the other cases. This case should be quicker, because if I'm in that case, what happens then here? So here, this is not, it's still the same, right? The same thing. But the thing is now that in the orange case, we know our induction hypothesis says that this is 0. We're in this case, so this is 0. So we know that this is 0, so 2 times 0, it is 0. So also this case works. Okay, and then finally the third case. So okay, I kept coloring a little bit, but I forgot the coloring. So this is the case, the orange case. So now we are in the purple case. So we have again that this is 2 times fn minus 2. But the thing is that the formula for fn minus 2 is different. How is the formula in the purple case? In the purple case, you have to add 1 to the exponent and then divide by 3, right? So it's 2 to the, take the n minus 2, add 1 to it and divide by 3. Okay. So what is that then? That is 2 to the power, it's twice this. I keep forgetting to write my 2 here. Twice that thing, so twice this thing, that is n minus 1 divided by 3. Now I'm multiplying this with 2, so I'm adding the exponents, so that is 1 plus n minus 1 divided by 3 is 2. It's 3 plus n minus 1 divided by 3, that is 2, n plus 2 divided by 3. Is this what it should be? Well, what should it be? Let's see what I predicted in my purple case. In the purple case is, if the index is n, then add 1 to that index and divide by 3. So now we are dealing with index n plus 1. What do we have to do? Add 1 by it and divide by 3. That's exactly what this formula says. So this matches too. Okay, this is quite long because of the fact that we have to consider various cases here. Okay? I just wanted to see, to make sure that you saw one of those. So I then quickly, the next ones are much quicker. So question C, there we had that f of 0 is 0, f of 1 is 1, and f of n is 2 times fn plus 1 for n bigger than 2. Right, that's the formula. Is this, oh, wait, what I wrote here, I said f of 1 is equal to 1, sorry about that. F of 1 is equal to 1. Is this well defined? Well, it's defined for 0, it's defined for 1. Is it defined for all numbers n? But look at what is happening here. In this definition, at least if I write it this way, I could write it the other way, but in this way, I seem to go find the calculation for my number comes from the next number. But if I don't have the number yet, how do I have the next number, right? This is recursion works always upwards. So this, the way it's formulated, it's not well defined. In particular, f of 2 is not defined. How am I going to find f of 2? There's no way from these rules that I can find f of 2. Because it's not 0, it's not 1, so it must follow from this thing here. Okay, and for this one, I don't have a formula. Okay, because this tells me this what information I have is that f of 2 is twice f of 3. Right, that's the information I have from this recursive step. But I don't know what f3 is, so how can I know f2? Well, you could say perhaps you have to calculate f3, but if you think about it, that requires f4. So I keep postponing, but I never get anything, right? Because I'm never going to give any of these higher numbers. So this is ill-defined. Again, this is not something I'm going to ask you, but it is good to know how these things work. All right? And now, let's do a simple one, right? So this is the case. This was 6D. F of 0 is 0. F of 1 is 1. And then the induction, the recursive definition is f of n is 2 times f of n minus 1 for n bigger than 1. Is this well defined? For n bigger or equal to 1, sorry, for n bigger or equal to 1. Okay, so, well, it says it includes n equals 1. So let's see what this rule says for n equals 1. If n is 1, according to that rule, because the rule applies it according to the instruction, the rule says f of 1 is twice f of 0. But that's not the case, because f of 0 is 0 and f of 1 is 1. So this is not right. So if I do this, what is happening here is that it's a very nice recursive definition. The fact is, my the information is not compatible. So there is too much in this case. Okay? I just want to point out that this can be. Now, what I want to do is, though, although this was the question, now imagine, so 6d bis, so a modification of that. Suppose the question was f of 0 is 0, f of 1 is 1, and f of n is twice f of n minus 1 for n at least 2. Okay, so you notice the modification, right? So I did a new question, and in the new question, I replaced the condition n bigger than 1, n bigger than 2. Do I have problems now? No, because now I'm never going to get myself, if I apply this rule here for n equals 2, then this tells me that f of 2 is equal to 2 times f of 1. And I know what f of 1 is. F of 1 is 1, so there's 2. Okay. Now you say, but the rule is wrong for if n is equal to 1, because n equals 1, we just figured it out. If you put n equals 1, it's not true. Yeah, but the rule doesn't say that you can do it, you apply it for n equals 1. So that's why there is no contradiction here, and that's why this is well defined. Now, this is an example of something that I might ask you to do, so I want to work out the details of it. So what's the formula? So the previous one, of course, since it was ill-defined, this was ill-defined, right? The original question, and therefore there's no formula, there's nothing to do, but here it is well defined. So let's work out the details of how to do this. So we know that f of 2 is 2 times f of 1, that is 2. What is f of 3? Well, f of 3 is 2 times f of 2, right? It's just twice the previous one, and that was 2, so 2 times 2, that is 4, and f4 is going to be 2 times f3, that is 2 times 4, that is 8. So what we see again is that we're going to get powers of 2, right? What are the powers of 2 that I get? Power 1 here, power 2 here, power 3 here. So it seems that the power that I'm getting is 1 less than my index. That is my conjecture. And that this is true for all n at least 2. It's not true for n equals 0. So my conjecture is wrong if n is 0. My conjecture is still right when n is 1, by the way. But that's okay, right? After all, I know f0 and f1. There's no need for me to calculate them. So this is a thing that this solves my problem. Now, proof. And here you can do proof by induction. You don't need strong induction because we only use the previous one. Okay, basic step. Well, we start from 2. So this is my statement, right? Pn is the statement that fn is equal to 2n minus 1. Okay? P2. Is P2 true? Well, P2 says, what does P2 say? P2 says that f of 2 should be equal to 2 times 2 minus 1, that is 2. Now, that is true because we just calculated that, right? That is here what we have. Okay. Induction step. So assume Pn, that's the induction hypothesis, right? Write it here, induction hypothesis, IH, to prove Pn plus 1. I can use strong induction, but you'll see it is not necessary here. Okay. Proof, let's carry out now the proof. Pn plus 1. Pn plus 1, what does it say? Pn plus 1 says that f of n plus 1 should be given by this formula here, and the formula says subtract 1 of your exponent. That's the exponent of 2. Subtract 1 from the index. So 2 to the power n plus 1, the index, minus 1. So 2 to the n. Question mark. Is this true? Well, what do we know? F of n plus 1 we know is twice f of n. That is using the recursion. So this follows from our recursive definition. Right? This is just using recursive definition, let me put that in purple here. Okay, this is from the recursive definition that we used. Now, we are now in the case Pn, the induction hypothesis, and the induction hypothesis says that then f of n, so now we are using this information, let's put it in blue, I'm using this information, start pushing the wrong buttons everywhere here, okay. I'm using this information, okay. And what does it say? That this is equal, so this is the induction hypothesis, this is equal to 2 times 2 to the n minus 1, right? That's what the formula says, 2 to the n minus 1, okay? So this is equal to 2 to the n. Are they equal? Yes, and I'm done, okay? So that was a couple of those. I know some of these can be quite lengthy, especially when they involve cases, and I'm sure you had a bit problem with the ones that involve cases. Then I want to do number 20. Number 20 is, I just want to show you that it doesn't always have to be about numerical functions. So it says, give a recursive definition of calculating the max of A1, A2, up to AN. So we're going to start thinking more and more in terms of programs again, of algorithms, right? As like in discrete one. So this will depend therefore on n, the number of inputs, okay? And so here's my recursive definition. Well, I have to do a basic step. And so if n is 1, that's the basic step, what do you have to do? I have to find the maximum of the number A1. Now, what's the maximum? If you have only one number, that's the maximum. So in n is 1, it's very easy to do. So what is the recursive step now? So this was the basic step, right? Recursive step. How do you define the maximum of these numbers? Recursively. There are a couple of choices, but recursion is a little bit, you have to be a little bit careful here with recursion. One of the right things to do is to say, well, let's take the maximum of the first n minus 1. So not taking the last one, okay? Now, the maximum, what can happen? Let's think about it. The maximum of this thing, it's either this maximum, or if it's not, it's the last one, right? AN. So to get the correct answer, I should also put AN here and take one more time the maximum. So this is what this question asked. And this is perhaps something that when you write an algorithm, this is exactly what you would, if you were, we have done this, right, in discrete one, to write algorithms for the maximum function, and this is exactly how it worked, okay? And so let me repeat one more time what we're doing. We're saying the maximum of n elements, you take the maximum of the n minus 1 first, and then that result, you know how to calculate it, that's recursive definition, this recursively you know what to do. You take now one more time the maximum between this element and that element. And that is, you take one more time the maximum, and that will give you the right answer. Okay? So that's a recursive definition of maximum. And this requires you only actually, of course, now you might say, well, but don't we have to explain what the maximum of two numbers is? Okay. So if you want to do maximum of two numbers, A1 and A2, then you have to define this. You say that that's A1 if A1 is bigger than or equal to A2, and it's A2 otherwise. So depending on what you want to take for granted, if you don't want to use max at all, and if you have to define max as well, then you have to also not just define what max of a single element is, but also what the max of a pair is. Max of a pair, which is what we know what it is, right? It's the first element if it's the biggest one, and it's the second element otherwise. All right? That's correct, right? And now I have everything, right? So the reason that I kind of need to include why do I need to include this guy here? Because, look, I'm using the maximum of two numbers here. If I have not defined this function max, then the program will not know how to carry out this calculation. Okay.